First of all, thank Professor Toyota for his kind introduction as well as his very valuable to me invitation to spend several weeks here at Osaka Prefecture University. It's gone by so quickly, it's hard to believe it's already been already 3.5 weeks. And soon I'll be saying goodbye to all of the people I've met here, which will be kind of sad for me, but maybe I will see some of you again in the future. So I've been lecturing to B3 and B2 students. I also did a lecture for freshmen and a lecture for M1 and M2 students. But in this final lecture today, I'm going to give a research seminar where I'll give you kind of an overview of one of the research projects that's going on in my group right now, being carried out mostly by doctor students and a few postdocs. So I hope you'll bear with me. This will be at a slightly different level, I guess, than my lectures, but I hope you will find it interesting. So as Professor Toyota said, today I want to talk about ylids of nitrogen, oxygen, and sulfur, and how those ylids can be used for the synthesis of target compounds, possibly natural product target compounds. And our thinking originated with the idea of building heterocyclic rings using these ylids, such as the nitrogen rings found in these alkaloids or the oxygen rings found in this polypyran segment. But as time went on, we also realized that the same chemistry might be used to make other types of rings, such as medium-sized rings, either made up of all carbon or maybe a medium-sized ether, such as the one shown here. So I'll sort of introduce the basic idea, our early results and what they told us, and then how we've tried to apply that chemistry. But before I do that, let me just mention that this is one part of what my group is doing. We have also projects underway, for example, in the area of the Nazarov reaction, which provides access to a variety of interesting polycyclic sort of products. And we're actually applying that Nazarov chemistry towards the natural product taxanine. And last time I was at Osaka Prefecture University in 2007, I actually talked about some of this chemistry. And so I thought I should talk about something different this time. We also have a project that is centered on the photochemistry of these compounds, which are called 2-pyrones. And these undergo a very interesting cycloaddition reaction photochemically to give 8-membered rings. And we're trying to use this chemistry towards this fusicoxin natural product, traversional. They also, these products undergo a very interesting transannular reaction to produce polyquinane ring systems like this. And we're trying to use that chemistry to make some of the simpler triquinane sesquiterpene natural products. Finally, today, I'll talk about this chemistry, which utilizes diazo compounds and transition metal catalysts to generate ylids, which can then rearrange and give us useful looking products like this. And today I'll talk a little bit about our progress towards these natural products. Back when I first started at the University of Utah, this was one of the ideas that we had. And the idea was, if we started out with an acyclic molecule in which we have a diazo compound and a an oxygen or nitrogen group at the end of the chain, that we might be able to convert this diazo intermediate into a metallocarbene. Well, we were confident we could do that. And what we were hoping was that this metallocarbene, which is quite electron deficient, would react with the lone pair on the heteroatom in such a way that we reach around and close a new ring. And now that new ring has a positively charged heteroatom and a negative charge here, either on the metal or on the carbon, depending on whether the metal remains associated with the ylid or has dissociated to give the free ylid. So we don't really know which of these is the eventual reactive intermediate. Certainly this must be the first thing formed, but it may be converted to this before the final step, which is the migration of this R1 group from X, from the heteroatom, to the neighboring carbon by either a 1,2 shift or a 2,3 shift to give us this sort of final product. So everything I've drawn before here is a short-lived intermediate. This is what we would isolate. Now I need to point out, I just sort of said, well, R1's going to migrate by a 1,2 or a 2,3 shift, but we need to keep in mind that how that migration happens will involve different mechanisms. So if it's a 2,3 shift, we should assume that this will be a concerted pericyclic mechanism where we form the new bond and break this bond at the same time. And that has stereochemical implications. If it's a 1,2 shift, most mechanistic evidence suggests that this is a stepwise mechanism, a dissociative mechanism, where first we break a bond, then we form a bond. And most evidence suggests that the way that bond is broken is by a homolytic mechanism where we have a radical on these two centers and we do a radical-radical recombination reaction. Now finally, let's take stock of what has happened. So we began with this acyclic compound. The former diazocarbon is now inserted in between R1 and X. So this red carbon used to be this one, and R1 and X remain attached to it, but not to each other. So it's as if we've done a CX insertion reaction, though certainly not by a direct insertion, rather by a stepwise process. From a bond formation standpoint, we've made two critical bonds, this carbon heteroatom bond and this carbon-carbon bond. And of course, because this is an intramolecular process, we have formed a ring, a heterocyclic ring, by this step right here. And finally, let me point out that this idea of generating a cyclic ylid from a diazo precursor plus some transition metal catalyst was first explored many, many years ago, mostly in the context of sulfur ylids by Professor Ando at Tsukuba University and by Professor Ojima, initially at the Sagami Research Institute, later at State University of New York at Stony Brook. And I need to point out their pioneering work into this sort of basic type of reactivity. We had some new directions we wanted to take this chemistry, especially with regard to oxygen and nitrogen heterocycles and exploring that 1,2 shift, which had really not been looked at very much.